So this is the notes about net ionic equations, which really the notes part of it is happening on the bottom half of page 9. And then I am going to do one example from page 11 at the top, or at least help you get started on it. Now, here on page 9, you see the title Net Ionic Equations, and you actually have a full problem set up and worked out using this process. And the whole idea with net ionic equations, if you actually look at this actual equation here, which is the net ionic equation we're trying to get to, this is the kind of important part of this double replacement precipitation reaction, is the part that forms our precipitate. So this is kind of just a simplified view of a double replacement reaction that focuses on the formation of the precipitate and what is actually participating in that reaction, because we're going to have some other stuff that's not actually really changing much, and we'll see that there, that we call spectators. So in this area where this problem is already kind of set up and worked out, I'd like to take some notes on what's happening here so you can see that happen before we do it. So first, a balanced equation. We've already kind of practiced writing these before. So the process here is to make sure to write out the formulas, all of your reactants and products. You see here in the initial question it was asking like what would happen, or will a precipitate form if solutions of potassium sulfate and barium nitrate are combined. So we write our potassium sulfate, barium nitrate, label those as AQ or S, then predict products and label them as AQ and S, and then balance that reaction. And you'll see all that we needed really to balance this one was this little 2 over here. So then in our overall ionic equation, which is really the first new thing we're going to do, what we're doing here is breaking up or ionizing anything that is aqueous, because this is saying that they're dissolved. If they are dissolved, then these compounds are not actually going to be staying together. All of the separate ions that we just put together into those compounds are really going to be dissolved and ionized in solution, if they're aqueous, that is. So you'll see here my K2SO4 has split apart into 2 Ks and 1 SO4 ion. They do have their charges written on them, and they still have that state of matter. Notice that the subscript K2 became 2K plus because those ions are separating from each other and from that SO4. So we're going to have 2 K plus ions floating around and 1 SO4 sulfate ion. We did not break up that sulfate because that was one of our special polyatomic groups that's on the back of the periodic table. Those never get broken up. Potassium and sulfate are the parts that separate, and because that sulfate didn't break up, I'm not going to be doing anything with that subscript that's a 4 here, because that's part of the sulfate. It's not becoming its own oxygen ion, so we're not going to move the subscript from that oxygen to the front. So breaking up everything that is soluble, notice my solid, which was not aqueous, was not soluble, did not get broken up in our overall ionic equation. Everything else did. Then, in order to actually form the net ionic equation, we're going to focus on that solid that's being formed and only keep the things that are used to make that solid. So we're taking our barium and our sulfate and forming that solid. All of that stuff comes into our net ionic equation, and everything else is basically going to come down into our spectator area. And you'll notice that these things, these spectators, were the same before and after our reaction. So we had those Ks and those NO3s were part of aqueous solutions before and after this reaction. And because they're dissolved in water, those ions aren't actually reacting at all. They're just kind of along for the ride. They're watching all of this net ionic reaction happen, but they're not actually participating in it. So if you've written your overall ionic equation, then you can look at that and see whatever is the same on both sides and pull that down into the spectator area. Or if you're focused on that net ionic equation, it's whatever isn't in that net ionic equation is going to become a spectator. And this is important because what this tells us is that the potassium part of that potassium sulfate wasn't important for this reaction. So if I was back in the back stock room or something trying to pull chemicals for labs and I couldn't find the potassium sulfate, but there was maybe sodium sulfate there, or even like lithium sulfate or calcium sulfate, the sulfate part of it is the important part for the reaction. So I could just switch out who's the spectator and it wouldn't change what we're observing in the reaction. It would look exactly the same. And I've had to do that a couple of times. So sometimes the labels on your bottles aren't exactly what we think they are just because I've had to make a substitution, but because I know that the thing that I was substituting for was a spectator, it doesn't change a thing. So let's actually go ahead and look and do one of these reactions together and go through this whole process. Actually, I always forget. I made that a little bit lighter, the stuff that was already written on the page, so you could maybe see this a little bit better, make sure that we got all of those notes down. And now, let's go on to working this one together. So, I'm going to help you out by telling you what ions we have here. If we're combining our silver acetate and strontium chloride, that'll help us write out our balanced equation, reactants, and products. As I can see here, when I put my silver with my acetate, that +1 and -1 just means that we need one of each. Don't have to cross-drop reduce at all. I'm going to leave a little space there for my state of matter. I always forget those. And then strontium chloride, my 2 is going to have to cross over when we cross-drop reduce. Technically, the 1 is crossing as well, but we wouldn't actually write that down. So SrCl2. And you might prefer to actually write those states of matter out if it's quick enough for you to flip your periodic table over and find it. I'm just trying to do all of this stuff at once. All of the same kind of stuff at once. So I'm writing formulas right now. Then my first product I'm going to be predicting is going to be Ag and Cl together, and those are +1 -1. And then I'm going to put my strontium and my acetate together, and that 2 is still going to be crossing over. It's just going to be crossing over onto the acetate. Actually, let me write this a little smaller. Okay, so I kind of sort of managed to squeeze that in. I always end up running out of space with these. Hopefully you can write a little smaller than I can on this screen. So I've written I've written my equation, and I'm going to now go back through and label them as aqueous and solid. So looking at acetate in our solubility chart, it's at the very, very top of the soluble section, and there are no exceptions. So this is aqueous. Chlorine is also in the soluble area, and strontium is not one of its exceptions. Now, if you wanted to save yourself some time and didn't want to have to do any work you don't have to, notice here that it told us that these are solutions. So if it's already dissolved in a solution, you don't have to ask yourself if it's aqueous or not. It automatically is. Now, chlorine is in that soluble section, but I just noticed when I was looking for strontium, it wasn't there, but Ag was. So Ag is an exception to that being soluble, which means this is going to be insoluble as a solid, and then our acetate is going to make this aqueous. So in our overall ionic equation, we're going to be breaking up everything except for this AgCl. So starting with our silver sulfate, we're breaking these right back up into their ions that they were before, giving them their state of matter. So having those written up top to help me write my formulas is also helping me not have to go back and check what are these charges, oh my gosh, and having to do the same thing over and over again. So strontium chloride is also breaking up. And this is one of those times, because I see my chlorine is going to be breaking off on its own, I'm bringing that subscript up to the front, because both of those chlorines are going to break off and be separate from each other and from that strontium. And AgCl stays the same. I just realized as I was doing this and checking my work that I didn't balance that equation before starting to break this up. So I'm going to take a quick moment to do that because we don't have to do a whole lot, but because of this 2 chlorines here, and I only have 1 there, I should have actually put a 2 here. That gives me 2 silvers, and that means I need to put a 2 here for that. So now I'm balanced, so 2 AGs, 2, yeah. So really what that means is that I should have a 2 here in front of my AG and my acetate, because that coefficient applies to both of these things automatically, putting a coefficient in front of that compound. And I'm also going to include that 2 here in front of my AgCl. And now I can continue on. I just have one more thing to be breaking up over here. So that's going to make strontium ion and 2 acetate ions. Ooh, barely managed to fit that. But that is our overall ionic equation. So now I like to highlight, or you could circle, the solid and the ions that are needed to create that solid. And our Ag from way over here. So I'm going to pull that down into this section. I'll use red. So net ionic equation is that 2Ag plus 1. That's a mess. And 2Cl negative 1 aqueous make 2 AgCl solid molecules. So that is our net ionic equation. Now, it might bother you a little bit that this doesn't look like it's fully reduced. We got 2, 2, 2 all the way across. But that actually just gets left like that because that is the proportions that this would be happening in our original equation. So we had balanced this correctly originally and reduced it down as far as it can go. But what we're understanding is that this is going to be kind of happening 2 at a time. For every molecule or kind of single reaction that we do, we're going to be getting the double amount of precipitate out of that. So that's our net ionic. That was most of our goal, but it's still important that we identify our spectators, and that's basically everything else. You'll notice it is the same stuff on both sides. Doesn't really matter the order. And now that we realize they're spectators, we don't really care how many they are, as long as we know what they are. So I'm going to say Sr plus 2 and acetate negative 1 are our spectators here. So it's really not too bad, I hope. That overall ionic equation is really the biggest, longest part of it. And that can kind of help you visualize what's happening and why that net ionic is what it is, and where those spectators came from. But especially in our lab that we did today, hopefully you're watching this after the fact and not before our lab, but the double replacement lab we're trying to just kind of real quick figure out what is that precipitate and what was the stuff that formed it, identifying those spectators. We didn't really want to have to go through that whole big long process, and I think that you could probably look at this equation, just the balanced equation, and you could probably, even without writing out the overall ionic equation, you could probably come up with that net ionic if you look at it carefully, because as we said on that last slide, the whole purpose of the net ionic equation is to make this solid. So if what you did after writing the balanced equation, that's still going to be necessary. If you started from knowing, okay, I'm going to be making 2 AgCl solid molecules. Now, what would I need from my original ingredients in order to make 2 AgCl molecules? Well, that'd be 2 of our Ag plus ones and 2 of our Cl negative ones. So you can probably go straight from that balanced equation to the net ionic and the spectator. And for our lab purposes, when we're doing a lot of these, that's probably the easiest way to do it. There will be one question on the test, though, that does ask you to come up with this overall ionic equation, show this whole process, do that file upload. So on the next couple of pages, I do need you to go through that process and practice that. But let's go ahead and look on page 11 and that first problem at the top. It's actually the second net ionic equation, our number 2. And I'm going to help you practice jumping from the balanced equation straight to the net ionic, because that's probably what you're watching this video for, is to get a little help with that lab that you're working on. So we're going to skip this for now, but come back and do this as practice, part of your practice doing that overall ionic equation stuff. Here are our ions, so I'm going to use those to write out my reaction real quick. Okay, so here's that overall reaction. All I did was take these numbers, cross drop reduce to find my reactants, and then I went back through and did that double replacement and got our copper with our sulfur for my first product, and then my ammonium and my chloride together for that second one. I've also gone ahead and checked what state of matter these would each be. So at this point I need to balance this, and my chlorines once again are going to be what I need to focus on balancing, and that actually is it. So now, in order to just skip straight to our net ionic equation, we're going to key in on our solid. I know the net ionic equation is what's going to form my solid from its ions. And this one is even simpler than the last one, because when this is balanced, we're just making one copper sulfide. So I'm probably going to need this copper ion and that sulfur ion, and I just need one of each. So I just need to make sure to remember to include that charge and the fact that they are aqueous. And that's my net ionic equation. And now our spectator ions are anything that is not part of that. And I find it easiest to look at the other product, because that's the stuff that didn't get included in our solid product. So here I can see that NH4 plus 1 and Cl negative 1. I can also see that here. If I've rewritten these and I'm focusing on these ions, these are the ones that are left out. So those are our spectators. So a lot quicker and easier. Honestly, at that point, what took up most of my time was writing that balanced equation and making sure each of those compounds was written correctly. So we got to bring back those skills. If you had them before, this is probably going to be a really easy topic for you. If you've still been struggling with writing formulas for a while, we've got to be able to get better at that.